us for this first video in chapter 9 where now that we were introduced to alcohols and especially how to make them in the last chapter, we're going to talk about the reactions that alcohols themselves can do and some other compounds or functional groups they could make. And one of those really important functional groups is ester. It's really an essential and an important functional group in nature. There's a lot more examples other than just this, like in antibiotic compounds and stuff like that. But for example, isopentyl acetate, this is really, if you smell the pure stuff of this, you would definitely recognize it as a banana smell. In fact, sometimes you find synthetic esters like this in some junk food candy that's banana flavored and whatnot. Trimyristin is a saturated fat that you find in nutmeg. And here's a really long ester molecule, and stuff like this constitutes the major component of beeswax. Okay, but these all have ester functional groups in common, and one thing I want you to note is that ester really is made from the alcohol, and you should always be able to find the alcohol portion. So here's the alcohol part, it's the carboxylic acid part. Right, they're made of alcohol and carboxylic acid combined. Here's the alcohol part, carboxylic acid part minus water is ester. Okay, so here's a more specific depiction of that. So here's alcohol, here's carboxylic acid. If you combine the two and remove this away as H2O, right, you will get an ester plus, of course, the water that's spitted out. Okay, so that's esterification in general, but what we specifically call Fischer esterification, not too surprisingly, sort of invented by Emil Fischer so many years ago, that same guy that won a Nobel Prize in chemistry for other stuff, involves catalytic amounts of some acid, strong acid typically. Okay, and that it's called Fischer esterification. Here's a great example of that with this is acetic acid. You might recognize that because in Gen Chem you probably had to memorize the polyatomic ion acetate. If you add a proton to it, that's acetic acid. Here's ethanol. Hopefully you recognize that by now, and hopefully you recognize that as sulfuric acid, which of course is a very strong acid. And this use of ethanol here is interesting because this is both the reactant and solvent at the same time. It fulfills both roles. Okay, and that will give us this ester that comes from the alcohol, that comes from the carboxylic acid. So let's take a look at the mechanism, which is one of those super important mechanisms. If we had time to do 2 ESAs in this class, right, like I think we would definitely have the Fischer esterification in the second one, but here's how the mechanism goes. So here's the carboxylic acid and the strong sulfuric acid, and because sulfuric acid is so strong, just it can deposit a proton H plus on just about anything that has a lone pair of electrons, like this oxygen. Okay, and so here's some proton transfer. Right, and and this is a really fast process. I think we talked about this once, but the acid-base chemistry, in other words, proton transfer, is the fastest reaction there is. So this is a very fast step that ends up with this oxygen being positively charged, right? And that's kind of special because that makes this carbon very electrophilic. Because hopefully you can imagine the other resonance structure where these pi electrons go to the oxygen to neutralize the oxygen, leaving behind a carbocation, right? So for that reason, that carbon is very electrophilic, right? Because of that, a very weak nucleophile like alcohol. Remember, alcohol is a weak nucleophile. It's not great. Can attack this very electrophilic carbon, like so, right? Because this has the resonance. It looks like that. Okay. Remember that arrow means resonance. That's not a reaction step. Now, this step is called a nucleophilic addition step. This mechanistic step. Okay. Now that leads us to this intermediate with a positive charge here still, right? Now, as you can kind of tell, this is a very unstable intermediate. And why is that? Well, it's mainly because the single carbon is attached to all these oxygens that are pretty bulky, and they're bulky because they got lone pairs. Remember, lone pairs of electrons take up a lot of space. That's what the sort of the message was from the Vesper theory that you learned in Gen Chem. And then not to mention there's this methyl group that of course also takes up quite a bit of space. So there's a lot of steric strain going on here among the electrons. Remember, lone pair electrons are more unruly. They take up more space than bonding electrons, which are kind of shepherded by two parents, so to speak, two atoms that are bonded together. Lone pairs, they're kind of like free-range kids. Okay, so this, we could say, is a very unstable tetrahedral intermediate. Mainly because just too many lone pairs. Okay, now what could happen here? One of the things I want you to keep in mind when you see these extra protons on a heteroatom, especially the extra protons that confer a positive charge, that's kind of not a unwelcome guest, right? Because of this proton, this oxygen is like forced to have a positive charge. So this is like a very unwelcome guest. And like you can imagine with an unwelcomed guest, they get tossed around from house to house. It's kind of sad, but kind of reminds me of the 1 week that was going to be kind of homeless during college. I had to like do the stereotypical couch surfing among friends, but after a while, like, you get tossed around a bit. Some of you might have an experience with that, but so this proton can move around on any heteroatom that has a lone pair. So at any given point, this proton might be on this oxygen or on this oxygen or on that oxygen. So that's what I'm depicting here as RPT. What does this stand for? Rapid proton transfer. Maybe I should say somewhere. that's kind of a abbreviation I might use a lot in the future, so please be aware. So at some point, the structure might look like this. Okay, now why is that important? Well, the moment that the extra proton is on this OH group instead of the ethoxy group, right? This electrons on the other oxygen could push it off, because now that makes for a really good leaving group. You could sort of describe this as the collapse of the unstable tetrahedral intermediate. Why did it become tetrahedral? Because you added a nucleophile to an sp2 flat trigonal planar geometry carbon. It became sp3 here and became tetrahedral, too crowded, right? So once that collapses, it kicks off something, and whatever you're kicking off needs to be neutral and stable, and now there is a stable leaving group. So maybe that's not. Right, you just kicked off water. That's neutral. Okay, so you could describe this as a collapse. Of tetrahedral intermediate step. Now this water, of course, could pick up the extra proton to make the product neutral, because remember, extra proton or unwelcomed guest gets kicked around, right? So that's your product. Okay, this structure right here. All right, now let's just have you answer this question. Hopefully you can predict the products correctly. We'll probably go over that in class. Now we also want to apply this same mechanism to the mechanism that we kind of left unanswered in the last chapter. Remember the oxidation of alcohols? There was we talked about the mechanism, and then we just kind of left this chromate ester formation mechanism steps as kind of blank, and so here we are filling in the blank. Now that we did the Fischer esterification mechanism, this should be piece of cake, or it should be the same, because here's alcohol, here's chromate that's already protonated. Now without the protonation, right, like imagine this is not there, this hydrogen, does it make sense that this looks kind of like carboxylic acid if you pretend the chromium is a carbon, right? That looks like this carboxylic acid. And remember, the first step was protonating carboxylic acid to activate the carbonyl carbon. So I've kind of cheated and have done that first step where the chromic acid might get protonated from like some other acids, like perhaps sulfuric acid. If you recall, go back to the chapter 8 notes, right? Alcohol oxidation typically involved, especially if you're using a harsh oxidizing agent like chromic acid, often involved sulfuric acid as well. So this proton could come from sulfuric acid the same way here. I've just done the first step for you just to kind of save time and space. Now once that happens, right, this carbon here is very electrophilic. I mean chromium, I should say. Right, for the same reason that we talked about here. Okay, so for that reason, weak nucleophile like oxygen is able to attack that, so that oxygen can become neutral. So that's a nucleophilic addition step. Okay. That will give us this intermediate. That makes sense. right? Now, at this point, right, you might be wondering what's going to happen. Well, remember, proton can be on any of these oxygens at any given time. Now, when it's on ethanol, the only thing that could happen is these oxygens kicking off the ethanol. That would get us back to the starting point and no progress. But when the proton is on one of the other oxygens, like say this one, right, that's just something that is happening all the time, whether you like it or not, rapid proton transfer of extra proton, right? Then you might have an intermediate that looks like this. Now you see a productive leaving group. And I say productive because if this leaves, the reaction can progress forward, right? One of the other neutral oxygens can push that off by reforming the double bond. Okay. Now, once that happens, right, we have a situation that looks like that, plus the water that you spit it out. Right, this is the neutral water that was kicked off. Okay. That will get us, and then water can mop up that extra proton, which will get us to this neutral ester of a sort. But that's not regular ester because instead of carboxylic acid, we had chromic acid. So what do we call this? This is our chromate ester. Okay. Now, why is this significant? Remember, if this is happening in like water or something, we could use another water molecule as a participant. And remember, it's when this proton at the would-be carbonyl carbon gets removed or eliminated that electrons flow in such a way the chromium gets to be reduced and therefore oxidizing the carbon. So this is the actual oxidation step that gets us to the aldehyde and chromous acid that's reduced, right? Remember, this is the reduced chromium. This is oxidized, right? And then this further gets oxidized eventually to become carboxylic acid, right? But I would refer you to the chapter 8 notes on this. Okay. I'll see you in the next